listen-only mode.
Good afternoon, everyone. I'd like to welcome everyone to our second webinar of the year. My name is Doug Lajan. I'll be hosting today's event. We're very pleased to have Andy Page with us from GP Allied, who's going to discuss bearing failure mechanisms. As always, UE Systems is looking for ways and venues to deliver valuable information to you, our users, out in the field. This obviously is a huge topic for many of you with your ultrasound programs. You know, how do bearings actually fail? And it'll help you do a better job of, by understanding that, it'll help you do a better job of applying ultrasound technology on your monitoring, your condition-based lubrication programs, your bearing programs, and a wealth of other applications for the tool. During the course of this webinar, you're welcome to email in your questions, and we'll be happy to get those questions at the end to Andy as we go along. If we don't get to all of your questions, please be patient. We'll certainly email you back the answers. There's only so much time we'll have at the end of the webinar for Andy to actually answer those questions live. So just a little bit about UE Systems. Been founded in 1973, 38 plus years of experience with ultrasound. Very large global footprint. You can see where we have locations available for both software and instrument support, as well as training, as well as a couple new offices that have just recently opened up. We've opened an office in the Pacific Northwest out of Seattle, Washington, and also one out of Calgary in Canada. So we're looking, obviously, to continuously offer the best service we possibly can to you, our users out in the field. The next slide is something new that we've introduced. It's called an interactive information kit. Each of you who attend the webinar, this will be emailed to you sometime after it in the next day or so. If you look at the interactive information kit, it has several buttons with information about our products as well as software downloads. And most importantly, look at the bottom right button, which actually gives you the ability to access many videos that we've done, case studies, certainly past webinars will be on there. It'll take a few days for us to get today's webinar up onto that interactive kit, but all of our previous webinars will be available, and also presentations from Ultrasound World. So I don't want to take up too much of your time, Andy. Let's all welcome Andy Page of GP Allied. I'll let him introduce himself and what GP Allied does, and we'll get the ball rolling today. Thanks for being here, Andy. Certainly appreciate it.
No problem. No problem. So I'm just going to share the screen here and make sure everybody can see the screen. Let me know if this doesn't show up. All right. That's everything showing up there?
It is.
Okay, super. All right. GP Allied, for those of you who don't know who we are a reliability consulting company, training company, and services company, headquartered out of Charleston, South Carolina, and we have offices in Brussels and over in Europe, and kind of a footprint around different places, but official offices Charleston and Belgium. So about 350 people in our company that we do reliability things, training, services, and consulting as well. So at GP Allied here, I'm the integration director, which means what we do in the field, what we say in the training class, and what our consultants are teaching and coaching. I try to make sure it's all the same thing. And some days it's pretty easy, other days pretty challenging because we got a lot of talented people who've got, their own experience and their own idea of how things go. But so, it's generally pretty exciting around here on a day-to-day basis. Today, we're going to be talking about bearing failure mechanism. And to talk about bearing failure mechanisms is to really talk about lubrication and how it works inside the bearing, and also to talk about the basic design of bearings. And from that, it will lead us into a discussion of how long bearings are supposed to last and the things that we do that accelerate the rate at which bearings fail. And all of this is to help us understand, from lubrication practices, alignment practices, preventive and predictive maintenance inspections, and just basic failure modes analysis, why all that works the way it works. And so in understanding the way a bearing fails, it helps us understand what our ultrasound instrument's doing, what our vibration analysis instrument is actually doing, what the thermography or oil analysis or even motor circuit analysis in certain instances, how it knows what it knows. So we found that, you know, getting a good understanding of the way bearings fail takes reliability people and maintenance people a very long way into understanding why all the other things you hear us talk about, or people in our business talk about, how it all fits together. So we consider this pretty much a fundamental class, if you will. So now it's labeled bearing failure mechanisms, but all the things I'm going to talk about in this presentation are exactly the way gears fail as well. Now, bearings are much easier to draw in PowerPoint, so the pictures will be around bearings. But just know that every time I say something about bearings, just in your mind's eye, picture it happening exactly the same way in a gear. And it's a little bit difficult for people who are new at this stuff to get their head around that bearings and gears fail the same way when mechanically they're so different. And what we're going to learn here is that with respect to physics, they're really not much different at all. So just know that every time I say bearing, I mean bearing and gear. All right. So let's get into it. The very first question you got to ask when you start to educate yourself about this thing is, how long are bearings designed to last? Now, when I ask that question in a live training class, we'll get any number of answers. You know, a couple of years, 10 years, or forever. These seem to be the three most popular answers. Year or two, you know, 10 years, and forever. So we got to look at this thing called L10 life. Now, the L10 life, I'll just go ahead and read it. The age to which at least 90% of a sufficiently large population of the same bearings under the same conditions can reasonably expect to survive. So the 10 in L10 doesn't mean 10 years, doesn't mean 10,000 hours. We hear that all the time. What it means is 10% won't make it to this life, whatever that life is. Now, the L10 calculation is a fairly straightforward calculation. It has to do with radial load, it has to do with speed, it has to do with lubricant type. And from that, we start to spec out the width of the bearing and the diameter of the rollers and a few other things that fall into the equation. But in essence, what we're trying to figure out is what's the right bearing for that application that will get it to a reasonable life. Now, for the people that study such things, what we know is that a bearing will last, in the absence of any of the problems we're going to discuss, a bearing will last about 5 times L10. Now, you can grab a book, you can look up the SKF, Torrington, whomever you buy bearings from. You can look up your particular bearing and you can find the L10 life. And the L10 life is always reported in hours. And in the absence of all the issues we're going to discuss, your expectation should be something in the neighborhood of 5 times that. Now, for most bearings, that's going to put you somewhere in that 8 to 12 year range. And 8 to 12 years feels like a lot for some people to swallow because they're used to replacing bearings in a certain application every year or every 2 years. And the organization has gotten used to that. And their maintenance budget has been adjusted to account for that. And their production schedule has been adjusted to account for that. So they've just gotten used to it. And that very thing right there is why we start this presentation with how long are they designed to last, how long are they supposed to last? Because we want to challenge that paradigm that, well, every 2 years they go bad and we replace them, and we've gotten very good at replacing them every 2 years. So, you know, that bearing is supposed to last 2 years. No, that bearing's supposed to last the same as everything else, about 5 times L10. If it's not lasting that, there's a problem. And it's some of those problems we're going to talk about in this presentation and how they manifest themselves in a failed bearing. Okay, so to understand bearings and gears, we have to understand lubrication because they are completely and utterly joined at the hip. You can't discuss one without discussing the other. So when we talk about lubrication, for any lubricant, as pressure goes up, what do you think happens to the lubricant? Now, this is generally where I'll ask, is lubricant compressible? And the answer to that is no, it's not compressible. If it were compressible, hydraulic brakes wouldn't work, hydraulic jacks wouldn't work, bearings and gears would not work the way they work today. So when we realize that lubricant's not compressible, then we got to ask ourselves, well, what happens to the lubricant physically when we put more pressure on it? We know the volume doesn't change. That would be the way we'd know it's compressible. So the volume doesn't change. So what physical characteristic happens to the lubricant when the pressure goes up? Well, what happens to the pressure when the pressure goes up? The viscosity goes up. And it doesn't just go up a little bit. It goes up exponentially. And when we get as high as 200,000 psi, most greases and some of your standard oils and stuff actually become harder than the steel they are servicing. Now, that's a bit tough for people who are new at this to swallow as well, but you put enough pressure on grease, that grease actually becomes harder than the steel it's touching. And it's that characteristic that makes bearings and gears work the way they work. See, when the lubricant's right, the roller never touches the race, or the two gears never touch. They're separated by this lubricant, and as the gear teeth mesh, or as the roller rolls into the load zone and the pressure goes up on the lubricant in between the roller and the race, it actually gets hard. And when it gets hard, it expands just a little bit, or just resists compression, compression, and it keeps the surfaces separate. So we'll talk about that. That metals never touch. So first, we'll talk about hydrodynamic lubrication. Hydrodynamic, one of those fancy words that the lubrication specialists like to throw out all the time. What we're talking about here is a journal bearing or a sleeve bearing. So there's a high conformity, which means large contact area. We have a whole lot of shaft that could be touching a whole lot of bearing. Now, when we have a large contact area, we're by definition going to have low contact pressure. Pressure and area are inversely proportional, right? So what happens then is, as the lubricant molecule is riding on the shaft, and as it goes into the load zone, and if you can see my mouse there, let's say rotation is this way, so the load zone is right in here, right? As it goes into the load zone, what happens is pressure starts to build on the hydrocarbon molecule. The hydrocarbon molecule resists compression, and it actually pushes back, and it's able to push back really hard. So as that molecule rolls into the load zone, an oil wedge is what it's called. An oil wedge is formed. Now, this oil wedge is harder than the steel, and it keeps the steel shaft and whatever the journal bearing's made of, it keeps them separate, doesn't let them touch. Now, as that molecule comes out of the load zone over here, the pressure starts to drop, and as the pressure drops, the hydrocarbon molecule doesn't have as much strength, doesn't push back as hard, and it loses its viscosity back down to its normal state. So the characteristics, the load characteristics, change as the shaft turns with respect to a given hydrocarbon molecule. Now, that's where the word dynamic comes from in hydrodynamic. Its characteristics changes as it moves in and out of the load zone. Hydro speaks to the fact that it's a fluid, right? So, so then it is the oil film that supports the load, not the bearing itself. The bearing supports the oil film supports the shaft supports the load. Contact pressure could be as high as 58,000 psi on some journal bearing applications. We're talking high load, high speed, like a turbo compressor or something like that. But typically, we're only a couple hundred psi. So this is hydrodynamic. So you need to associate the phrase hydrodynamic, or the word hydrodynamic, with journal bearings. Now, the concept is very, very similar when we go to rolling element bearings, but we have some big changes. One, it's a very small contact area, which means I have high contact pressure. We still have the oil wedge between the surfaces. The oil film still supports the load, but contact pressure is much, much higher. It could be up as high as 450,000 psi. So we still have the the liquid hydro. We still have the dynamic characteristics of the lubricant. We still have that oil wedge forming as it goes into the load zone, and when it comes out of the load zone, the oil wedge dissipates, and so on and so forth, right? But we have an extra word here. We got this elasto thing, right? So this elasto, exactly what you think it means, elastomeric or elastic, right? So you're asking yourself, what inside a bearing would have an elastic property? And in actuality, it's the races themselves. As that oil wedge passes through the load zone, everywhere, if you could freeze that situation in time, and we got a graphic of this coming up, but if you could freeze that situation in time, you could actually see that the face of the race, just under the roller, just right directly beneath the oil wedge, the face of the race is compressed. And then when that oil wedge passes by that spot, that face springs back up. And as the next oil wedge comes by, basically the next roller comes by, that spot gets compressed. And when it passes, it pops back out. So this is why we say the steel has an elastic property. When the oil wedge passes, it compresses. When it goes by, it pops back out. Right? So elastohydrodynamic. So associate the word elastohydrodynamic with rolling element bearings. So we still have the oil wedge. We still have the oil film, lubricant film, keeping the two metal surfaces separate. So it works the same as in a gear as it does in a bearing. All right, now, so let's actually get some bearing drawings up here. They're pretty gross, but they work. All right, this is an approximation of a bearing. So when we take that bearing out of the package, we can rattle it a little bit, and it shakes because everything's loose in there. But when we install that bearing on the shaft, probably one of the most common ways is that the inner collar gets expanded, and as it expands, it expands the inner race, and we take a lot of that sloppiness or that play out of the bearing as we install it. Now, when we turn that bearing on, when we turn that shaft on and it starts to spin and it's holding the dynamic load of the rotor and the shaft and all that other business, then we get that compression we were just talking about. So if you could freeze all of these rollers in time, you could see, we could measure the compression of the outer race. And the same thing's happening on the inner race, by the way, in the load zone. So it doesn't push in quite this much. We're only talking 3 to 5 microns deep, maybe 10 in the worst case, 10 microns. So we're not talking very deep into the steel, but that's where it begins, and that's where the compression happens. Right? So if we were to take a picture from the side, here's our inner race, and here's our ball or our roller, and here's our outer race. Then we look at rotation. If the inner race is rotating this way, the roller is going to rotate that way, and our high pressure areas are where the oil wedge is going to form. So you can, this is much larger than it actually is in real life, but this is done for illustration purposes. You can see the oil wedge there forming in this high pressure area, and then over here in this high pressure area, we get another oil wedge. So you can imagine then this roller rotating in between these two oil wedges, and it's the oil wedges that keep the roller from touching the inner race and that keep the roller from touching the outer race. So this is probably the best picture of elastohydrodynamic lubrication right here. Now, again, we could be as high as 450,000 psi up inside the wedge. That's where the pressure's measured, inside the wedge. So that is where the lubricant characteristics change, viscosity goes out the roof, and that's what makes it hard enough to actually keep the races and rollers separate. This is fundamental in understanding the way bearings and gears fail. Now, if we were to freeze one roller in time, we could measure the force directly beneath the roller. Directly beneath it, it's the highest, and if we move a little bit left and right, it's a little less. If we move a little bit left and right, it's a little less, a little less, a little less. For those of you who are would-be physicists, this is called a Hertzian stress model. Now, every roller has a stress cone, if you will, that it takes with it as it rotates around the inner race, inside the outer race, especially specifically as it goes through the load zone. So if we were to watch this spot right here, where my arrow is, we can imagine that it's relieved, but the moment this roller goes on top of it, it compresses, and then when it gets in between, it relieves, and then it compresses and relieves. So let's watch that. So if I set my arrow right there, so relieved, compressed, relieved, compressed, relieved. So as you're sitting there picturing, okay, wow, all of the rollers as they pass through the load zone, they're carrying that stress concentration with them, and we get compression relief, compression relief, compression relief, compression relief, and it just goes on and on and on forever. So then you start asking yourself, wow, I guess I can kind of get how physically a bearing cannot last forever, because that stress concentration with each roller as it comes through the load zone is moving through there, right? And we all know if we go out into the shop or if we go home and we get a wire coat hanger, or we go out in the shop and we get a thin piece of metal and we sit there and bend it back and forth, we don't have to bend it back and forth very many times before we get fatigue. We get that it starts to crack internally, and then eventually it cracks completely. Well, bearings are no different. Right? It just happens to take a lot of cycles for it to happen. If we ask ourselves, how often does this happen in a day? Well, on a 1,775 RPM shaft, we're about 29.6 rotations per second. And those of you who are vibration trained understand this next one. In one rotation of the inner race, 8.193 balls or rollers will pass a given spot in one rotation. So if we were to look and say, okay, how many times does that one spot in the load zone get compressed and relieved in one day? It's 21 million times. Over the course of a year, it's 7.6 billion times. So then you ask yourself, wow, it's any wonder that they last 5 times L10, which puts you in that 8 to 12 year range for most bearings. So when you take 7.6 billion times 8, that's a lot of compression cycles, a whole lot of compression cycles. So, there's no way it'll last forever. So physically, what happens inside the bearing when we start to get this thing called fatigue? Well, it works exactly like this. It looks exactly like this. We call this subsurface fatigue. So you can imagine roller after roller after roller coming by and compressing that spot, and then it relieves, and compressing that spot, and then it relieves. And this happens a couple of billion times a year. If it's 7.6 billion if it ran 24/7 all year long. And after a while, the surface of the race literally starts to exhibit what's called rolling contact fatigue. Now we'll leave all the fancy stuff for the AST people, but we'll just call it subsurface fatigue. And if you've ever taken a bearing apart and you could see that discolored track that runs right down the center of the race, you can see it, but you can't feel it. What you're seeing is this subsurface fatigue, and for those of you who've never seen it, it looks like this. So you see the discolored track that runs right down the center of the race, both the outer race and the inner race. That's subsurface fatigue. And if you go to Radio Shack and you get you one of the little $10 microscopes that takes a AA battery, you can set it right on the race there, and you can focus it, and you can actually see these subsurface cracks. Now, the good thing about steel, and most things in general, if you're only talking 5, 6, 7 microns deep, it's transparent. You can actually see the cracks, but you can't feel them. And that's why we can see that discolored track on the race. Now, if I allow that to keep going, eventually all those cracks will connect. So it's still called a subsurface fatigue, but we can throw the word advanced on there if you like. Now, what's interesting here is the energy being given off by this subsurface fatigue, as you might guess, is extremely high frequency, super high frequency. And that is why the ultrasonic instrumentation picks it up so well. Every time, you can imagine, every time a roller passes here, we get compression and we get relative movement inside the crack. So every time we have small motions under high stress, the frequency will always be high. If we had large motions under low stress, then it would be very low frequency. But we don't have that. It's very high stress. Nothing has broken loose yet. So as that roller passes by and puts a lot of strain inside those cracks, and those cracks start to move, sides of the crack move relative to one another and they're scraping against each other. That's that super high frequency stuff that the ultrasonic stuff picks up very, very well, very, very well. If you have a modern vibration analyzer, something that's capable of envelope demodulation, you can turn that on and you can hear this as well. Well, you can't hear it, but you can see a spectrum and waveform of it, right? So the cracks connect, looks like this. What happens next? We leave those long enough. Oh, by the way, if you want to see the vibration data for that, it looks like this. December 9th of 1997, there was no problem. January, the subsurface fatigue began. February wasn't much different. March, the subsurface fatigue moved to advanced, and you could actually see the time waveform. You can see it starting to happen. So took the bearing out, got some cool pictures of it. Okay, so if we leave that subsurface fatigue long enough, eventually all those little cracks connect, and when they connect, chunks of things start popping out of the race. Now I can feel it with my finger. Now I can hear it when I walk up next to it. And the worse the spalling gets, the easier it is to hear it. The easier it is to feel with the kind of the naked hand, you know, if you lay your hand on the bearing. And we call this spalling. So pieces pop out of the surface of the race. Now, here's the interesting part. Once the spalling occurs, it accelerates very quickly from there. It doesn't work much different than your tire in your car going into a chug hole or pothole in the road. It doesn't just fall in smoothly and come right back out smoothly, does it? No, it usually falls in, and then when it hits the other side over here, it knocks a bigger chunk out. Well, no different in a bearing. Remember, the oil wedge is dependent upon a small contact area. So what do you think happens when this oil wedge comes off this ledge here? The contact area gets much larger, relatively speaking. And it's much more difficult for the lubricant wedge to maintain its shape because the pressure's off, or, you know, a certain degree of pressure is off. So we lose our ability to keep the surfaces separate because we now have a larger contact area. So as the roller's moving along here, it's knocking little asperities off, little chunks off, and then when it hits here, it's a pretty rough ride for it. It works just like the tire on your car when it goes into a pothole. It's going to knock a chunk off, and pretty soon we got it back to a high pressure area, and the oil wedge forms back up. But you know, we got all the other rollers behind it doing the same thing. So that's why our old faithful P to F curve is a curve, not a line. It takes a while to go from here for this to form, and it doesn't take near as long for it to go from this to that. And then it doesn't take near as long to go from that to this. And then once it gets this, then more spalling happens much more quickly. Right? So we got to ask ourselves, well, here's some examples for those of you who've never seen spalling. This is a I wouldn't say it's a mild case, but it's not severe. It's severe from a vibration standpoint, an asset health standpoint, a maintenance standpoint. But you know, we've all seen bearings with much more severe case of spalling than this. But that's what spalling looks like. There's the vibration data for it, by the way. May of 1996, it's there. June, it's significantly worse. Replace the bearing and it's gone. Right? If you're wondering what they look like, this is what they look like. So contact fatigue, spalling, pitting, benelling, fretting, it goes by different names, but it's all wide, thin pieces of metal that have popped out of the inner and outer race. And of course, once it begins, it accelerates very, very quickly. So we got to ask ourselves then, where's our first sign of trouble? Well, our first sign of trouble is this subsurface fatigue. Right? Now, a lot of people ask me, well, can oil analysis find subsurface fatigue? And I just simply ask them, well, what has broken loose in the bearing that you would find in the oil? And they go, well, nothing's broken loose yet. Well, then how can you use oil analysis and expect to find subsurface fatigue when nothing has came loose yet? You can't. Now, so this is a good learning point for vibration analysis, oil analysis, infrared, motor circuit analysis, ultrasound. there's no one test that does everything. But when you start thinking about all those different tests and how they act in concert, the way they act together, we start to be able to paint a very comprehensive picture of the health of the piece of equipment. And it realizes it takes more than one inspection method to find all the things that we want to find on our equipment. And it's in understanding how bearings fail, we start to create more realistic expectations of, one, our bearings, two, our inspection program, and how they're able to find things. For example, very common practice, old school common practice for determining whether or not a bearing is damaged is something the old timers called a lift check. They would go out, place a dial indicator on top of the shaft. The machine shut down, but they'd place a dial indicator on top of the shaft. And they'd put a crowbar or something directly underneath it, and they would pick it up. And they would expect to see the mounted clearance of the bearing, which is going to be 1 to 1.5 mils per inch of shaft diameter. And if they didn't see any more than that, then the old timers would claim, oh, nothing wrong with this bearing. It's got the exact amount of, quote, wear it's supposed to have. Well, if you had subsurface fatigue, it wouldn't result in any additional clearances inside the bearing because nothing has worn away yet. Right? So using an old school lift check is not really going to help. A bearing's got to be severely spalled out before that lift check is going to produce more than the mounted clearance of the bearing. So what we've discussed then is the mechanical way a bearing fails. In a moment, we're going to discuss the chemical way a bearing fails. So realizing this is our first sign of trouble, we go back to our old faithful P to F curve. Subsurface fatigue puts us very near point P. So if our inspection programs are designed to find these defects very close to point P, then we've just organizationally we've bought ourselves something very valuable, something that most maintenance planners and supervisors and engineers claim they never have enough of, which of course is time. All right, so this is the value of condition monitoring, if you will. Now, things that we can do as owners and operators and maintainers of assets, things that we can do that would accelerate the fatigue. Or let me put it this way, things we shouldn't do because it accelerates fatigue. Anything that has to do with the radial and axial load of the drivetrain is going to accelerate fatigue. So allowing a machine to run out of balance gives me a higher radial load. Allowing a machine to run misaligned gives me a higher radial and axial load. Installing V-belts too tight, having broken bolts, loose bolts, broken welds, all of these things produce a very high radial load on a machine that wasn't designed for that high radial load. Overloading the machine itself, overspeeding the machine, or shock loading the machine. All of these will result in a higher accelerated rate of fatigue. So you can imagine then if every 6 months or every 8 months in our 8 to 12 year period we experience one or more of these accelerators, then there's no way the bearing will last as long as it's supposed to last in that application. It's about 5 times L10. So the business case then for helping an organization understand to not allow these things, or upon finding them, get them fixed quickly, is that every one of these is taking that mean time between failure for the bearing, and the longer these are, the more severe they are, and the longer we allow them to stay in the machine, our mean time between failure is just continually dropping. Okay, so that's the mechanical aspects of how a bearing fails. Let's talk about how a bearing fails chemically. And some of you may be going, well, wait a minute. What do you mean chemically? There's no chemicals in a bearing. Well, actually there is, and there is a chemical reaction that happens inside a bearing that is supposed to happen, right? Any mechanical engineers online, especially those who've taken machine design or specialize in machine design, understand that bearings are supposed to be the sacrificial lamb of any rotating machine. Case in point, most power plants in North America. My numbers may not be exactly accurate, but I'm pretty sure the average age of power plants just past 60 or 65 years. Right? So same turbines, same pumps, but they've been very well maintained. Right? Bearings were replaced when they were supposed to be replaced, and as a result, no housing damage, no shaft damage, no impeller damage, that kind of thing. Right? So that's a really good analogy or case in point about how bearings are supposed to be the sacrificial lamb of a machine. And here's what I mean by sacrificial lamb. There's probably a lot of people on the line who have installed bearings, and if I were to ask you what happens to the temperature of that bearing right when you turn it on, everybody always says, well, it climbs up higher than we expect it to be normal, and then after an hour or two, it settles right back down to normal temperature, and that's where it stays. Exactly. So let's talk about why that happens. If I were to take iron and steel, for instance, if I were to take steel and oxygen and heat and throw in a little bit of grease, what do I get? Well, what I get is a thin film of iron oxide. Now, when I say thin, I mean only 1 to 3 microns thick, not very thick at all. And what happens is, like I said, that's a result of the heat, the lubricant, the oxygen, and the steel itself. So this lubricant wedge then rides along on this thin film of iron oxide. Now, you can imagine when your hands are dirty, if you rub them together, what falls out are little bitty balls of dirt, and then eventually, if you keep rubbing, you'll get little bitty balls of skin. That's exactly what happens in a bearing. As this lubricant wedge, which remember is very, very hard, as it rides along on top of this lubricant film, it's not just skating right along and everybody's happy. No, it's actually rolling up little balls of iron oxide. These are called spheroids, and you can actually get a picture of them in your oil analysis. They're about 5 to 9 microns in size, and they could be as high as 15, depending on characteristics or whatever. But they are normal wear particles in a rolling element bearing and a gear. And all it is this iron oxide film rolling up. Now, you can imagine if I'm rolling up iron oxide, what's happening down here at the bottom with the interface of iron oxide and steel? Well, when that gets thin enough, the oxygen and the heat and the steel and the lubricant interact again, and I just peel off another layer of parent metal to keep my iron oxide film about 1 to 3 microns thick. Right? So as this thing rolls by, it's rolling up those little balls, and it's continuously rolling it up, and it's continuously reaching down and grabbing another layer of parent metal to keep that iron oxide film about 3 microns thick. This is what the people who study such things call delamination. We're just removing one layer at a time. One layer, next layer, next layer, next layer. Right? So the best example of this would be we were measuring vibration at a plant, and we'd been there a long, long time. And this one particular pump never had any problems. But over the course of the years, we could see the vibration data showing that the bearing's just getting progressively more and more loose, which is exactly what happens here. We're eating away at the inner and outer race, so you can imagine the internal clearances of the bearing. The internal radial clearances of the bearing are getting bigger and bigger as each moment passes. Right? Now, how long should that take? Well, we monitored it for the better part of 12 years, and there was no record of it ever having been worked on. And finally, in year 12, the looseness had gotten to the point where, we were like, look, you really don't want to let this thing run any more loose than it actually is. It's time to fix it. And they fixed it. So, just in that particular plant, it was something of a luck thing, but that one of them had ran 12 years. But that was the cool thing, is here's real evidence that how bearing is supposed to fail, right, in the absence of all these other things. So if we think about accelerators, now that's called adhesive wear, by the way, two-bodied wear. So I've got the roller and the race, and they're both the same material, and they got that little dynamic there, and they're rolling up those little spheroids grabbing another layer. So this is called adhesive wear. So when we put lubricant in there that's too light for the job, then the oil wedge is not heavy enough to do its job. When we put lubricant in there that's too heavy, literally the molecules are a little too big to go in there and make that oil wedge the way it's supposed to work. And of course, water at room temperature is not compressible. But inside a lubricant wedge at 250,000 plus psi, that water is certainly not room temperature. It's water vapor, and water vapor is very easily compressed. So this is what's known as the saturation point of lubricant. It's the percentage of water in the lubricant where EHD, or Elastohydrodynamic Lubrication, is not possible. Basically, how much water can the lubricant hold before the lubricant wedge cannot form. Right? So that's adhesive wear. So what if we put a piece of dirt in here? So here's a piece of silica, common dirt, right, or a big element of common dirt, and it only has to be thicker than 3 microns for it to make damage. And the smallest particle we can see with the naked eye under ideal light conditions is something in the neighborhood of 40 microns. So it's very easy to have dirt in the bearing that's big enough to cause problems, but still smaller than we can see. So you can imagine if this lubricant wedge grabs a hold of this piece of silica, it doesn't just knock it out of the way. It actually grabs it and plows with it. And this little arrow here is meant to represent the wear particles that are coming away from this piece of dirt being drugged through the outer race and grinding that piece of parent metal out. If you're wondering what they look like this. Known as curls or corkscrews or long needles. These are all abrasive wear mechanisms, abrasive wear particles. And they're anywhere from 5 to 100 microns in size. And it's pretty bad when that starts happening to your gears or bearings. That just means you've got some contamination in there, abrasive contamination. And with these pressures that we're talking about, even soft metals, soft contaminants can be abrasive because of the pressures we're talking about. Right? So things that we do that accelerate abrasive wear, allowing blown seals to be there. Poor lubricant handling practices, usually we're the cause of how contaminants got into the reservoir. Poor lubrication procedures and the way we top it off and the way we don't clean the zerk fitting when we attach the grease gun, and all these things that you've probably heard or learned about in lubrication classes. So these are things that we do that accelerate the rate of abrasive wear in there. Now, the SKF is often misquoted. They're not the source of the problem. They just happen to be the source of this quote. They actually said bearings have an infinite life, or bearings can have an infinite life, and usually people stop there for some reason. Well, what they said was when particles larger than the lubricant film are removed. Well, remember the lubricant film is only 3 microns thick. So it's in a grease lubrication application, it's pretty much impossible to keep contaminants larger than 3 microns out of the bearing. With oil lubricated stuff, it's pretty easy to filter down to that level, but grease, it's pretty difficult. So I'm going to end the presentation. We got about 15 minutes. I'm going to end the presentation with a few examples and how you can use some of this information to your advantage tomorrow in your plant. Was working with a gold mine, and this guy had some bearings that they had removed as a result of their vibration program, and he was kind of showing me some of his war trophies, we call them. Now, if here's an inner race, we know that the ball sits there, and we expect the subsurface fatigue when it begins to go right down the center of the race, something like that. So this would be normal. Well, he brings me one that looks like this. Now, for those of you who are not familiar with this, you could sit there, imagine turning this inner race in your hand, and you can see this line moving left to right, left to right, left to right, right? What this is the result of misalignment. So the shafts could be misaligned, or in this particular case, the bearing was misaligned to the shaft. So when they installed the bearing, they didn't ensure that the bearing was sitting square on the shaft. And that's what caused that particular failure mechanism. failure pattern. He brought me another one that looked like this. Now, those of you who are watching, it should be in the center, but it's pushed off to the side. Well, this is called axial loading, and the particular root cause of this one was they took 2 bearings out of the box. Each bearing had an expansion ring. They didn't know that for 2 bearings on the same shaft, you only need 1 expansion ring. The other one you can throw away. Well, they figured, well, both bearings came with expansion rings. I guess we'll put them both in. And they put them on the outside of both bearings, and what happened is as the shaft got hot and expanded, and all shafts do.
This is Julia.
As the shaft expanded, it bowed in between the expansion rings, which caused axial loading of the roller up on the edge instead of in the center where it's supposed to be. Now, here's the interesting part. Here's the reason I bring this up. I said, have you shared this with your crew? And he goes, no. I said, let's do that, man. There's some valuable information here. He goes, well, you know, you explain it pretty well. You do it. I said, okay, cool. So we got the crew together, and I said, look, we don't know what machine this came off of. Don't know, don't care. Don't know who did it. Don't care. I said, I just want to show you what you can learn if you pull these bearings, cut them apart, and just spend 5 minutes looking at them. And we talked about how to make sure a bearing is square on the shaft, and we talked about expansion rings. And 2 mechanics stood up and said, hey, that's actually us. And I was like, hey, whoa, I wasn't trying to get you to testify or anything. And he says, no. He goes, this is important. He goes, nobody had ever taught us how to check to make sure the bearings sit and square on the shaft. Nobody ever taught us about the proper use of expansion rings. He goes, what you just said, he goes, that's more than I've learned in the last 10 years working here. He goes, in fact, I can take you to 4 other fans that have the same exact problem as these because we've worked on them in the last 3 months, and we didn't do these any different. We did, you know, the ones in your hand. And I'm like, whoa, all right, good. Now, that was the learning point at a craft skills level, at the crew level. The bigger learning point for everybody on this call is, had I waited, had that organization waited until they could feel that bearing and it was rough, or until they could hear it, or until it heated up, where do you think this evidence would be? Right? These tracks here on these races that's evidence. That's evidence of poor, incorrect installation practices. It's just subsurface fatigue right now. That's where the evidence is. If we allow it to spall, then what happens is I'll get spalling all the way around the race, all the way through here, and I will lose that pattern. I'll lose my evidence. So there is a very big business case to identifying these defects high up on the P2F curve and then getting them out before they're hot to the touch, before you can hear them from the parking lot. Because if I can get them out in time and I can cut them apart and spend 5 minutes looking at it and spend 5 minutes reviewing it with my crew, man, there can be a lot of learning going on, because we can figure out who's got the skill set and knowledge, who doesn't have the skill set and knowledge, and who just, was kind of in a hurry. And that is where we can start to make some big step changes in the performance of, our equipment. Another example. You guys may have seen this. Now, I had to draw this in PowerPoint, so these ovals are a little bit bigger than they normally are. But this wasn't just through the load zone. This was all the way around the outer race, just continuously, and all the way around the inner race, continuously. And it's not subsurface fatigue. These are actually indentations. And for those of you who've never seen this, this is actually called electrical fluting. This is a little bit different than a variable frequency drive motor that's grounding through the bearing. That's not what this is. What this is the motor has an electrical problem, and it's actually trying to beat its bearings out because it's vibrating at some electrical frequency, which is 2 times line frequency. Right? So in ultrasound, this would make a very pretty sound because it would be very even, very symmetrical. It wouldn't sound like your typical spalling in a bearing fault, which has very random, very rough sound. In ultrasound, this had a beautiful sound to it. I wish we had a recording of it, but we didn't. But the problem was the ground wire on the motor had corroded away. and most people didn't think anything of it because they're like, oh, it's grounded through the electrical system. It's not a big deal. In actuality, it's a very big deal. Now, the learning point here is, especially with mechanics and electricians and operators and people who walk by these motors on a daily basis, you pull this thing out, you cut it open, and you show them that, and you show them a picture of the corroded wire before it was repaired, and you say, look, when you see this going on with the wire, this is what's going on inside the bearing. Right? These are connected. That's not just the, oh yeah, one of these days we'll have to come by and fix that ground wire. You know, it actually matters a lot. And so we can connect some very nice dots in people's minds in the plant by being able to show them these broken bits and show them these bearing failure mechanisms and connect them to actual real-life practices like the last example or real-life conditions like this example. Okay. Last one, for those of you, you're sitting here looking at this thing. Now, the vibration data just shows that there's a bearing fault. Right? It was there on the first reading in December, and it wasn't there. It wasn't much worse in January, and then, of course, sometime in January or early February, it was repaired, and you can see the bearing frequencies are there. Now, here's an example of what I'm talking about. This one had another one of these things right here. We cut one off and didn't cut the other one off. And you should be able to note that there's severe spalling going on right here. But what you probably are seeing as well is, why is the spalling just here and not uniformly across the width of the roller? Well, that would be the effect of misalignment. Misalignment is going to cause that spalling to happen up where the load is actually pushing between the roller and the race, as opposed to a uniform load all the way across the roller and the race. So this is a very interesting example of spalling as a result of misalignment. All right, now leave it much longer, and that spalling is going to work its way all the way across here. It'll be very hard to see this misalignment pattern. Right? So here's the idea with educating ourselves about bearing failure mechanisms. I mean, we've all seen the P to F curve, and some of you may even seen the I to P to F curve. Right? So this I to P interval, notice it's flat. The I to P interval is said to be the defect-free period. Right? Now, unfortunately, on some machines, that's only 30 minutes or so. Right? But it should be 8 to 12 years for our bearings. So the whole idea of understanding bearing failure mechanisms is to, one, get a very good feel for how our condition monitoring technologies are working and what it is they're actually looking for. And then two, take that information and translate it into different actions on a daily basis with our craftspeople, with our operators, with our engineers and technicians, and create a situation where we're extending I further back, extending that I to P interval as long as we possibly can. And it's not till we educate ourselves about the way bearings fail that we start to get a clear picture in our mind of how to do that. I think philosophically and intellectually, we all understand and agree that we want to extend I to P. But I think a lot of people sit there and go, okay, yeah, I agree that we should do that, but I don't know that I know how to do that. And when we start educating ourselves about the way bearings fail, it becomes, as we say, painfully obvious what has to be done. And it becomes much easier to get it done, right? So you can imagine two pieces of equipment. One has a long I to P interval, the other one has a short I to P interval. So the difference between these two is kind of the value of, and you could insert just about anything here, the value of condition monitoring, the value of precision maintenance, the value of root cause analysis, the value of reliability. Stick anything you want in there, it'll work. Right? So that's pretty much the presentation. Doug, did we have any cool questions that come in that we could answer in the next 5 minutes?
Yeah, I got a couple, Andy. Thanks for that, by the way. That's a great presentation. Just a couple questions from some people in the field here. When you're talking about things like those subsurface cracks, what's the minimum rotational speed that you could pick this up using ultrasound, vibration, anything like that?
That's a really good question. That's a question we get a lot as well. I've personally done, the slowest shaft I've done is 8 RPMs, and in a race fault, just clear as a bell. And the slowest one I've ever seen presented at a conference was 1/3 of an RPM.
Okay.
So in essence, there's really no lower limit.
Okay. Another one here. Will using high-quality lubricants help extend the life of bearings, like, for example, soybean lubricants?
Well, you know, we get that question a lot, not about soybean lubricants, but about, you know, your custom blends and your synthetic lubricants and stuff like that. And the answer is, you know, maybe. It depends on what problem we're trying to solve. For example, if the predominant issue with my bearings are balance and misalignment, there is no money I can spend on lubrication that will fix that, or that will even help that, or even affect that, right? Now, if you say, well, you know, our biggest problem is our viscosity index improvers are depleting too quickly. Sure, you could spend some money on a custom blend, get you something with more VI, viscosity index improvers in it, and that will get you better performance. So, you know, a lot of people think, well, if I just spend more money on oil, I'll have less bearing failures. Not necessarily the case. If it's a alignment, fits, and tolerances problem, you can put whatever you want in it from a lubricant standpoint. It's not going to help, right? Or if it's a contamination issue, right? You say, well, you know, we grind this or do that here, and we got, you know, blown seals all over the place because of poor lubricant practices and lots of contamination going in. There is no lubricant you can buy that will solve that. So before you start spending money on lubricants, high quality lubricants or custom blends or synthetic lubricants, you need to be absolute sure what failure mechanism is that's causing this, what the root cause is, and can a better lubricant solve it?
Okay. Another one here, Andy. What's the good operating temperature for a grease lubricated 1800 RPM motor bearing over ambient temperature?
Whoa, boy. Talk about a loaded question. There are too many other parameters to talk about. I mean, the material of construction plays into effect here. How much air is moving across the surface plays into effect here. The humidity of the air plays into effect here. So I'm not going to fall into the trap of spitting out a number so that people can, you know, I was on this webinar thing, and he said this, and blah, blah, it's wrong. So that's I'm not going to do that. But I will tell you that across the board, you know, kind of the 80-20 thing, right? So if we embrace the 80% and we say, you know, most bearings, motor bearings, and now the old school was, can you put your hand on it and leave it? Because if you can put your hand on it and leave it comfortably, it's not, quote, too hot, unquote, right? Now, okay. So you can put your hand, most people can put their hand on something and leave it comfortably at around 150 to 155 degrees F. Now, I don't suggest you do that. I mean, that's just an unsafe practice because you don't know if that bearing's got a problem, and you could about to lay your hand on something that's 300 degrees, which, you know, has been done. So for $69, you can get a spot radiometer at any hardware store, and you can measure the temperature of something for next to nothing. That's the way it should be done. But if somebody's going to make me put a number on it, I don't know about over ambient. I just know that skin temp around 150, it's going to be rare that there's actually a problem, especially at 1775 or 1800 RPMs. It varies greatly with shaft speed. Right.
One more question here, Andy, and then for those of you who didn't get your questions done on air, so to speak, we're certainly going to get all these questions that you emailed in over to Andy for him to answer. So sorry about that, Mr. Page. I'm going to give you a little more work to do after doing the webinar. But last question that I did want to ask here is, in gears, do the subsurface cracks only happen on the rolling point of the teeth?
Oh, no. The rolling point of the tooth, you got to look at the way that the two teeth interact, right? So there's the rolling point, or what some people call, there's a specific name for it, I forget it, but something volute of the point. So the teeth are not triangles, right? They're like triangles that are bulged out in the center, right? So you know, it starts deep in the root, if you will, not all the way in the root, but it starts on the back side of that curve, and then the two curves match, and then it comes out the other side. So if you could look at the gear tooth profile and see the fat portion of the tooth, it's the fat portion, front to back. It's the fat portion, or inside to out, rather. It's the fat portion where the rolling element fatigue, a rolling contact fatigue in this case, rolling contact fatigue will occur.
Okay. Super. Andy, do you mind giving out your contact information for those people who would be interested in getting in touch with you directly with some questions or?
Don't mind at all. apage@gpallied.com. I thought I had it on the last slide, but I've messed up here. No, I don't. So apage@gpallied.com. I'll do it right here. Sorry about that. Thought I had it on there.
That's all right. Just so everybody can have a chance to ask some questions. And I'll forward these questions to you, Andy, that we got to answer. Again, for those of you who didn't get a chance to have me ask the question live, you're welcome to email Andy. Email's right there on the screen, apage@gpallied.com. Certainly also welcome to email us at info@uesystems.com. Well, thank you very much, Andy. Certainly appreciate you spending some time with us today.
No problem. Enjoyed it.
It was certainly a great webinar. You know, for those of you who are interested in more presentations of this type, I think there's actually a couple of GP Allied people going to be down at our conference in May. So certainly think about joining us at Ultrasound World 8. We're going to have all kinds of presentations on equipment reliability, ultrasound, infrared, complementary technologies. So we've got a really good program set up for this year. You can also certainly consult our website, uesystems.com, for application information for some of our training courses that are coming up in the future. And save the dates. April 25th, we're going to have another webinar. It's somewhat related to this, creating superior return on investment through aggressive contamination control, which is going to be presented by Mark Barnes of Desk Case. Then in May, we've got Ultrasound World, and then the week after Ultrasound World, May 23rd, we're going to shift gears a little bit for those of you who are into the energy management side, and we're going to do a webinar, Advanced Trends in Compressed Air Best Practices. So again, thanks everybody for tuning in. We had a great turnout. Thank you, Andy. Everyone, take care. Have a safe day.
Okay, thanks.